In the last lesson we looked at the very basic tools that we need to start to investigate flowing water. In part 1 we looked at the essential flow parameters. In part 2 we looked at how to classify flow. And in part 3 we brought all of these ideas together to look at the principle of continuity. And for almost all of lesson 1 we were looking at examples of open channel flow. In this lesson we're going to start to look at the physics of moving water in a bit more detail, and we're going to do that by looking at pipe flow. The reason we're starting with pipe flow is because pipe flow is actually slightly more straightforward to analyse than open channel flow. That's because for pipe flow, the area of the pipe is fixed. So when we're considering the continuity equation, one of those variables, the area, is known and fixed, and that makes our life a bit more straightforward. So as we're starting to look at the physics of exactly how water flows in more detail in this lesson, we're going to start with the easiest example, which is pipe flow. Let's consider a simple example of a pipe flow. Imagine a pipe coming out of a tank that's filled with water. Here the depth of water in the tank H is going to drive water through the pipe and cause a flow. However, rather than just try to imagine this with a drawing, I've built a model of this system to help us visualise it slightly more clearly. We can think of this system as a reservoir feeding a supply pipe, and in this example we have a water level of approximately 125 mm above the outlet pipe driving the flow. If you were an engineer building this system in the real world, the first thing you'd need to know is what the discharge coming out of the end of the pipe is going to be at a given water level in the tank. So let's have a go to see if we can work this out using the theory that we've discussed from the last few lessons. The depth of water in the tank is 125 mm. But when we're doing calculations, we'll need to quote this level in meters. We know that discharge is the velocity in the pipe times by the pipe's cross-sectional area. The pipe has a diameter of 15 mm, and we'll also write that in meters. And we can work out the area of the pipe because we have the diameter. The area of a pipe is pi r squared, and the radius is half of the diameter. So we can work out the area of the pipe, but the issue here is we still have two unknowns in the continuity equation, velocity and discharge. So we're going to need to find another way to work out the velocity in the pipe before we can work out discharge. We can do this using a framework called Bernoulli's Equation. If this is the first time you've ever seen this equation, it might look quite complicated with lots of different terms, but to get us more familiar with it, we're going to spend a bit of time now working through each of these terms. We could do this by showing how the equation is derived with several pages of maths, but actually we can derive this whole equation just by looking at the system that we've been thinking about and thinking about exactly what is going on inside the tank. Let's start by considering the system when the valve on the end of the pipe is shut, so we have no water flowing in the system. If we imagine a particle of water at the base of this tank, when the valve is shut, the particle will be stationary, but as soon as we open the valve, the particle will accelerate down the pipe and go shooting out the end. The question is, what is it that's giving this particle of water the energy to move down the pipe in the first place? For a particle at the base of this tank, the only thing that could give it energy is the 0.125 meters of water above it. So it's actually the pressure from the water directly above the particle that's going to force it to move down the pipe when we open the valve. The pressure of water on a particle in a body of water can be given as pressure equals rho GH, where rho is the density of water, g is acceleration due to gravity, and h is the height of water above the particle. This gives us a pressure in newtons per metre squared. However, in hydraulics we normally quote pressure in units of height. If you think about our tank, this actually makes perfect sense, as all of the energy in the tank is coming from that 0.125 meters of water depth, and the height of water is the only variable affecting the pressure, as density and gravity are both constants. So we can rework this formula for pressure into units of height, and this gives us an expression for pressure in units of height as pressure in newtons per meter squared divided by the density of water and gravity. This particle has the equivalent of 0.125 meters of pressure trying to push it through the pipe. It's important at this stage to consider the concept of the conservation of energy. Every particle in this tank actually has the same amount of energy as every other particle. The form of energy may be different at different points in the tank, but the total energy of any particle in this tank is going to be the same. If we think of a particle at the surface of the tank, this particle has no energy due to pressure, as there is no water pushing down on it, so the energy from pressure for this particle would be zero, but it does have the same amount of energy as the particle at the base of the tank. If we took a pipe from the surface of this system, by the time the pipe reached the base of the tank, this particle of water would be travelling at the same velocity as the particle at the base of the tank moving through a pipe at the base. Just think for a moment what form of energy this particle at the water surface has. This particle has 0.125 meters of potential energy from its elevation, because it's elevated 0.125 meters above the outlet pipe, which is the datum of this system. We'll denote elevation energy with the letter Z, and elevation energy is already in units of meters, so there's no need to do any conversion. What about a particle that's exactly in the middle of the tank? What energy does this particle have? This particle will actually have a combination of pressure and elevation. It'll have 0.0625 meters of pressure from the water pushing down from above it, and 0.0625 meters of elevation because it's this high above the datum. We could actually write an expression for the total energy of a particle anywhere in this tank when the valve is closed. When we are quoting energy in units of meters, we call it pressure head, and we can use a capital H to describe the total pressure head in a system. So at any point in this tank when the valve is shut, the total pressure head will be the sum of a particle's elevation and its pressure, all in units of meters. So, a particle at the base of the tank will have 0.125 meters of pressure and 0 meters of elevation, giving a total pressure head of 0.125 meters. A particle at the water surface will have 0.125 meters of elevation and 0 meters of pressure, and a particle right in the middle of the tank will have 0.0625 meters of elevation and 0.0625 meters of pressure, again giving a total pressure head of 0.125 meters. So in this tank we have a total pressure head of 0.125 meters, and this water really wants to get out of the tank. If you've ever had a leak in your house, you'll know that water is really good at finding a way to flow. And when I built this tank, I had to be really careful to make sure that it was completely watertight at this pressure. In the pipe, we have 0.125 meters of pressure really trying to force its way out of the tank. We can't see the pressure in the pipe as easily as in the tank, as here the water can't find a free surface like it can in the tank. But we still have that 0.125 meters of pressure pushing against the pipe wall. We could actually see this pressure if we were to drill a hole in the pipe and install a gauge. The water would now find a free surface in the gauge and show us the pressure in the pipe, which is the same as the pressure in the tank. So why is the water not flowing at the moment? Water always flows from a point of high pressure head to a point of low pressure head, so we always need a pressure difference to make water flow. And here, when the valve is shut, there's no pressure difference, because the valve is pushing back against the fluid with the same pressure that the fluid is pushing against the valve with. But if we take the valve off the end of the system, we now have a case where there is a pressure head difference. Now we have 0.125 metres of pressure head trying to force water out of the tank, but nothing pushing back. We now have a pressure difference at the outlet of 0.125 metres, which is going to drive this flow. We call this pressure difference delta H. This system is now actually a great example of unsteady flow, because as the water flows through the pipe, the tank will empty and the pressure driving the flow will drop. But for the next few lessons, I really want this flow to be steady with a constant water level, giving a constant pressure head driving the flow. So I had to make this tank into something called a constant head system. This was done by having a supply pipe that's constantly adding water to the tank, and then an overflow pipe which keeps the water at a constant level. Returning any excess water back to the sump. So as we can see, we now have a constant water level in the tank of 0.125 metres, and water is flowing because we have a pressure head difference. There's 0.125 metres of pressure head trying to force water out of the pipe, but nothing pushing back, giving us a pressure difference delta H of 0.125 metres. It's not actually true to say nothing is pushing back at the pipe's outlet. We actually have atmospheric pressure pushing back, which is a far greater pressure than the total pressure in the tank from water. But we can actually neglect atmospheric pressure because it's acting at all points in the system equally. Atmospheric pressure is pushing back at the outlet, but it's also pushing down on the water surface in the tank. If we formulate this mathematically, we can see that even though atmospheric pressure may be significant, it cancels out in the equation. The reason we can almost always ignore atmospheric pressure is because normally it acts equally everywhere in the system, so it's always on both sides of any pressure difference equation. In this series of lessons, we'll always assume atmospheric pressure is zero for this reason. So now we have a constant water level in the tank, giving us a pressure difference that's driving this flow. But now we have moving water in the system, we need to revisit our total pressure head equation, as we now have another form of energy in the system. As we open the valve on the system, we can clearly see that the pressure in the pipe drops, as energy in the form of pressure is converted into movement or kinetic energy. And if we take the valve off the pipe altogether and let the pipe flow unrestricted, we can see that almost all of the pressure is now converted into kinetic energy. So we need to add a term for kinetic energy to our equation for total head. Kinetic energy in units of meters can be written as velocity squared divided by 2 times gravity. So at any point in our system, a particle can have 3 forms of energy: elevation, pressure, or velocity head. And its total pressure head is the sum of these 3 forms of energy in units of meters. This is Bernoulli's equation, and this is the equation that we're going to focus on for the next few lessons. But the question is, can we use this equation to work out the velocity in our pipe, remembering the question that we set at the start of the video? The key to this process is to remember that for an ideal system with no losses of energy, total energy is always the same at all points in the system. So if we consider any 2 points in this system, the total pressure head is going to be the same. Energy can convert between the 3 different types, but the sum of all of the 3 energies at any point in the system will always be the same. So the total pressure head at any defined point 1 in our system will be the same as the total pressure head at any defined point 2 in our system. And in our system, the total pressure head is always going to be 0.125 meters. Let's apply Bernoulli's equation between the water surface of the tank and the outlet of the pipe. So point 1 is the water surface of the tank. And point 2 is the outlet of the pipe where we want to calculate the velocity. So U2 in this equation would be the velocity that we want to calculate, which is the velocity of water as it leaves the pipe. So we finally have an equation with U2 in the equation. But the problem we have is we still have 5 other variables in this equation: Z1, P1, U1, Z2 and P2. And the equation looks quite complex and intimidating to solve in this form. However, if we think about this system, it's actually a lot simpler to solve this equation than it looks. Let's start by thinking about point number 1. Think about a particle of water at the surface of this tank. What form of energy does it have? Well, the particle has no pressure, as there's no water above this particle pushing down on it. So we can say the particle's pressure at this point is 0. So we can cancel the pressure term out of the first half of the equation. It also has no velocity, as we can assume the velocity of the water surface of this tank is negligible compared to the velocity of the water in the outlet pipe. So we can also cancel the kinetic energy term out of the first half of this equation. So the only term we have in the first half of the equation is the elevation term, which confirms what we know, which is that at the water surface of the tank, all of a particle's energy is potential energy from its elevation. How about if we do the same process at the pipe's outlet, where the water is leaving the system and returning to atmosphere? Here the elevation term will be 0, as we're at the base of the system, so there's no potential energy, so we can cancel the elevation term from the second half of the equation. There's also no pressure at this point in the system, as the water is returning to atmospheric pressure. There's no head of water pushing down on any of these water particles as they leave the pipe, so we can also cancel the pressure term from the second half of the equation. So we can now see that the first half of the equation at point 1, all of the energy is in elevation, and the second half of the equation at point 2, all of the energy is in velocity. So we now have an equation with only 2 variables in it, and we know that the elevation at point 1 is going to be 0.125 meters. So we can rearrange this equation for velocity. and assuming acceleration due to gravity is 9.81 meters per second squared, we get a final velocity of 1.57 meters per second. Now that we've worked out the velocity, we can return to the continuity equation and finally find out the discharge in the pipe. By multiplying the velocity that we've just calculated by the area of the pipe, we get a final discharge of 0.278 litres per second. So we started with a massive equation, but actually, because we were able to cancel out most of the terms in the equation, it ended up giving us a relatively simple expression to work out the velocity in this system. The final thing to do is to check if our theory matches reality. We used the velocity that we found from Bernoulli's equation in the continuity equation to get a final discharge of 0.278 litres per second, which is suggesting that 0.278 litres is leaving this pipe every second. So let's actually measure the discharge and see how the real discharge compares to our prediction. We can do this using the method described in Lesson 1 Part 1, by timing how long it takes to collect a certain volume. For this flow, I collected 0.85 litres in 4 seconds. Which gives us a discharge of 0.21 litres per second. This is really pretty close to what our calculation gave us, and would certainly do as a great ballpark estimate of the system's discharge. However, it's clearly not exactly correct. The predicted discharge, where we're using Bernoulli's equation to find the velocity, is about 20 to 25% larger than the actual discharge in the system. Have a think about why the predicted discharge, using the assumption of the conservation of energy, might be larger than the actual discharge in a system like this. We're then going to talk about this fully in lessons 3 and 4. So if we want to find the velocity in a system, we can do this by applying Bernoulli's equation between 2 points in that system. The key to this process is finding 2 points where you're able to cancel out every term apart from the known terms and the one unknown we're trying to find. This can take a bit of practice for more complicated systems than the one we've considered in this video. It's also worth understanding the assumptions we're making in this process. Here we are assuming conservation of energy between 2 points. That is to say that there are no losses of energy between point number 1 and point number 2. Essentially, this means we're assuming the fluid is ideal, which means we're neglecting the effects of friction and viscosity, which in the real world will lead to losses. Assuming no losses of energy works fairly well for small systems like the one we've been looking at in this video, but for systems with longer pipes, the effects of friction and viscosity will become non-negligible and we'll need to account for them to get accurate results. So in summary, we have discussed that a fluid can have 3 forms of energy: elevation, pressure and kinetic. And in hydraulics we will quote these forms of energy in units of meters and we call that pressure head. This gives us Bernoulli's equation, and for an ideal system with no losses, the total energy is always the same between 2 points in this system. So we can apply Bernoulli's equation between 2 points, and as long as we end up with only one unknown, we can find out what that unknown variable is. When we apply Bernoulli's equation as we have in this video, it will allow us to work out the velocity and discharge in a pipe on the basis of a known pressure difference. In the next video, we're going to look at this equation again, but instead of working out velocity in a pipe, we're going to use it to work out what the pressure is at a certain point in the pipe.